So let's pick up where we left off last time. We were talking about rules for aromaticity here. We had these two rules that a molecule has to follow in order to be classified as aromatic. It has to be a fully conjugated ring, meaning a ring of sp2 hybridized carbons, and there has to be an odd number of delocalized electron pairs. All right, so we got 5 examples down here. Everybody take a second and go through and classify these as being either aromatic, non-aromatic, or anti-aromatic by applying those 2 rules that we discussed above. All right, so let's start to go through these here. All right, we'll do this one first. I need to see if this satisfies rule 1. Do I have a fully conjugated ring? All right, so I need to identify my sp2 hybridized carbons. Well, any carbon about either one of these double bonds will indeed be sp2 hybridized. But then I get to this top one up here, and this is not sp2 hybridized, but rather sp3 hybridized. And so that's going to break my conjugation in my ring. So I do not have a fully conjugated ring. I'm not even going to go on to rule 2 here. I can say that since this one fails rule 1, it is non-aromatic. All right, let's jump over this complicated one for a second and go to the square here. Okay, now do I have a fully conjugated ring? All right, so again, I'm going to highlight each carbon about my double bonds, and boom, all my carbons in my ring are sp2 hybridized. All right, so satisfies rule 1. Now I got to move on to rule 2. How many pairs of delocalized electrons do I have? Well, both of these pi bonds here will be delocalized, so that's 1, 2. All right, so do I have an odd number of electron pairs? No, I have an even number of electron pairs, so this satisfies rule 1, but fails rule 2. This is anti-aromatic. Okay. All right, these fused rings here can be a little bit harder to see, but we're going to play the exact same game here. Do I have a fully conjugated ring? Well, I'm going to color my carbons about those double bonds. I get to these ones at this intersection of these two rings. Well, there's a double bond here. So that means both of these are indeed sp2 hybridized. Right? These are about a double bond. These are about a double bond. So are these ones. So do I have a fully conjugated ring? Yeah, I have this massive set of conjugated carbons here. So now I'm going to go through and count how many delocalized electron pairs I have. 1, 2, 3, 4, 5, 6, 7. So do I have an odd number of delocalized electron pairs? I do. So this molecule here would be classified as aromatic. All right. So now we're going to move on down here. Now I have this carbocation in my ring. All right. So first of all, let's apply rule 1 here. Do I have a fully conjugated ring? I can see that all of these carbons are indeed sp2 hybridized because they're about those double bonds. But then I get to my carbocation here. All right, so is my carbocation going to mess up my conjugation of my ring? So real quick, let's just review carbocations. Carbocations are a little bit weird in that every other element very strictly follows its octet rule. But carbon, being the least electronegative of our nonmetals here, will sometimes exist in this high energy intermediate we call a carbocation, where it's got these 3 bonds. All right, it's only got 3 bonds, no lone pairs. All right, so it doesn't have a complete octet, and instead what it has is this empty p orbital. All right, so there's nothing sitting in that p orbital, unlike our other sp2 hybridized carbons in our molecule, but nonetheless our carbocations are indeed sp2 hybridized. All right, but importantly, because that p orbital is empty, there's no electrons that it's adding to this ring here, so they do not add to your electron total. Okay, so the bottom line is if we look at this molecule here, we're trying to figure out if we have a fully conjugated ring. We get to our carbocation and we say, yes, indeed, carbocations are sp2 hybridized. Okay, so that means that this pair of electrons here is going to be able to fully delocalize around that ring, including into that empty p orbital. All right, but now when we go and we count our number of delocalized electron pairs, we got these pi bonds here, 1, 2, 3. Importantly, that carbocation isn't bringing any electrons to the game here, right? So that's not going to contribute to my total number of electrons at all. I only have these 3 pairs here. So then what would we classify this molecule as? Aromatic, right? It satisfies rule 1, that carbocation doesn't break our conjugation. And we got an odd number of electron pairs, so rule 1, rule 2, aromatic. All right, so then take a second if you have not already and classify this one for me here, another carbocation ring. right, I'm going to go around my ring, circle my sp2 hybridized carbons. Do I get to color the carbocation? Yes. Again, that one is sp2 hybridized. So boom, I got a fully conjugated ring. But how many electron pairs are there delocalized about this ring? Two. So that makes this compound anti-aromatic. Okay. All right, so we have these two rules that we apply to our molecules to classify them as being either aromatic, non-aromatic, or anti-aromatic, right? And that's pretty straightforward in terms of applying these two rules. All right, so now let's talk about what it means to be aromatic, anti-aromatic, or non-aromatic. All right, using what are called molecular orbital diagrams. All right. So what these diagrams help us to explain are that aromatic compounds are super stable. All right, so benzene, for example, we said was like our classic aromatic compound. All right. Well, if we took something that looked very similar to benzene, cyclohexene, what will we classify cyclohexene as functional group-wise? What functional group do I got here? Alkene. All right. So cyclohexene with its double bond, a normal alkene, we can react these with, for example, hydrohalogens, and we get our addition reactions. Get an H on one side, a bromine on the other side. All right, so our alkenes, they undergo addition reactions. All right, benzene looks a heck of a lot like an alkene, right? It's got a bunch of carbon-carbon double bonds, okay? But we're going to throw this into a different category, which we're calling these aromatic molecules, because benzene and other aromatic molecules do not undergo addition reactions. In order to do so, it would have to break the aromaticity of that ring, and it's not going to do that, all right? Because again, aromatic compounds are super stable. So those double bonds do not behave the same as our alkenes. That's why we put them in a separate category. All right, anti-aromatic compounds are super unstable. All right, it is very hard to create an anti-aromatic compounds. Molecules will kind of go out of their way to not be anti-aromatic, having more reactions, okay? So aromatic means your compound is super stable. Anti-aromatic means that it's super unstable, all right? So why is that? How can we start to explain that? What we're going to do is we're going to use these MO diagrams here. All right? So let's take an example. Let's start with our classic aromatic compound benzene. All right, so in molecular orbital theory, your atomic orbitals mix together to form bonding orbitals. What we call molecular orbitals. Importantly, the number of atomic orbitals that you mix is going to equal the number of molecular orbitals you get back out. All right. Half of those molecular orbitals are lower energy than the atomic orbitals. And half are higher energy. Which we call antibonding orbitals. All right. Okay, so molecular orbital theory is a quantum mechanics-based theory. This is not a quantum mechanics course. We do not have the math credentials to be actually doing the math behind this theory here. So what we're going to do is we're going to create this sort of diagram that illustrates what's going on in our molecular orbital theory, all right? And a big question is, well, how the heck did we know that that was the diagram to make? Because that's what quantum mechanics tells us, all right? And again, we're not doing the ugly behind the scenes math. We're trusting the big brains in the quantum department, and we're going to use these diagrams to illustrate our aromaticity and anti-aromaticity, okay? So in order to create this diagram, what we're going to do is we're going to take our molecule here, all right, all of our molecules have these little shapes to them, these little polygon shapes. All right, we're going to turn that shape so that we have a corner pointing down. All right, in the case of benzene, at least how I typically draw it with the point down anyway. So all I'm going to do is I'm going to take my molecule here, and I'm going to just turn it into a hexagon with that point facing down. Boom. All right, we're going to add this y-axis of increasing energy. All right, and now we're going to draw in our molecular orbitals on this diagram at every corner. All right, so what do I mean by that? I'm going to add an energy level at this corner on the bottom. I'm going to add an energy level at each corner as I move up. And then I have another one at the top here. All right, so my little hexagon that I started with is really just to help me figure out where these various energy levels should be. I got one at the very bottom. I got two tied as I'm moving up, another two that are tied, and then one at the very top here as well. All right, and what we're going to do is we're going to fill in this diagram with our delocalized electrons. All right. So how many delocalized electron pairs do we have?
3.
Right, we have that odd number, that's what made it aromatic. So then how many total delocalized electrons are there? There are 3 pairs of them, 6. So I'm going to put 6 electrons in my diagram here, all right? This is very similar to what you learned how to do back in general chemistry with the 1s2, 2s2 business where you draw the arrows in. Remember, each orbital can fit 2 electrons, 1 spin up, 1 spin down, and we always fill from the lowest energy level to the highest energy level, right? So we're going to start down there on the bottom. All right, so when we're filling in our delocalized electrons, we got some filling rules here. 2 electrons per orbital. One up and one down. We always fill from lowest to highest energy. All right, but then there was one more filling rule that we had for orbitals that had the same energy, which is going to be important here because now we get to this next layer and these two are tied, right? Same energy level. Okay, remember you half fill equal energy orbitals first. Before adding that second electron. All right. So, importantly, I got how many more electrons to add to the board here? 4, right? 2 out of my 6 are down. I need 4 more. When I fill in these next 4 electrons, I'm going to half fill these orbitals first, and then I can go back and double up. All right, remember, half of our orbitals that we've created are low energy bonding orbitals. The other half are those high energy anti-bonding orbitals. So we can see in this case here, all of our electrons now live in these bonding orbitals in our molecular orbital diagram. All right. Cool. So we're going to sort of revisit this and talk a little bit more about this and what feature it has that makes me know that this is an aromatic compound. But let's get another example here. Using the same set of rules, you're going to create an MO diagram, but this time for cyclobutadiene. All right, we're going to do our square. All right, so step one, I got to take my shape here. Oops, that's not what I want to do. All right, but importantly, we draw our square here as this, but we got to turn it such that we have one of those corners facing down. All right, so when we draw our polygon to represent our energy levels, we got to have one of those corners facing down here. All right, now we're going to draw in our energy levels at each one of these corners. So we have one down at the bottom. We have two tied here in the middle. All right, and then one here at the very top. All right, how many electrons am I going to put into this diagram? 4. So we're going to start at the bottom. 1, 2, pair those up. But now when I get to this next energy level, I got to go through and half fill each one first. And now I'm done. All right, so let's just kind of take these two here and compare them. All right. Let's remember this first one was for an aromatic compound, benzene. And what do we know about cyclobutadiene? Aromatic, anti-aromatic, non-aromatic. Anti-aromatic. All right. All right, so our aromatic compounds will always have fully filled bonding MOs. They're anti-aromatic. In this case, these ones are kind of right on that line between bonding and anti-bonding. But really the important key here is that anti-aromatic compounds will always have these half-filled molecular orbitals. Remember that second rule that seemed like it kind of came out of nowhere, that you had to have an odd number of electron pairs? Well, if you have an even number of electron pairs, when you go to fill in your molecular orbital diagram, you're always going to have these unpaired electrons here. Okay? These unpaired electrons are the key to why these anti-aromatic compounds are less stable than we would expect. All right, so unpaired electrons are what we called paramagnetic. Meaning that they interact with a magnetic field. All right? Well, remember what it means to be conjugated, right? Do these electrons stay put in our conjugated ring here? No, what's going to happen? They're going to delocalize, and they're going to be able to delocalize around the entire ring here. Okay? So it turns out that when charges move in a circle, they create an electric field, magnetic field. All right, so our delocalized electrons are creating a magnetic field. So you have this molecule where these electrons are moving around and creating this magnetic field, but because those electrons are unpaired, they're interacting with that magnetic field in a way that raises those electrons' energy, right? So it's the interaction between our paramagnetic electrons and this magnetic field that gets created by that anti-aromatic compound. That is what leads to our increase in energy here. All right, so the interaction between those paramagnetic electrons and this magnetic field raises the energy of an anti-aromatic compound. All right, we simply just don't have that problem with our aromatic compounds because they always will have fully filled molecular orbital diagrams, so their electrons aren't interacting with any magnetic fields at all, right? Everything's all paired up, so there's no interaction. Anti-aromatic compounds will always have these unpaired electrons in their MO diagrams, and that's what leads to that instability of that anti-aromatic compound, because those unpaired electrons will interact with the magnetic field created by those delocalized electrons. Okay? It's not a super satisfying explanation, I'm going to be dead honest with you, but that is that is the theory of why anti-aromatic compounds are much less stable. And again, importantly, we can illustrate that using these MO diagrams here. All right, so last kind of compound that we got to talk about here in this anti-aromatic aromatic discussion are what are called heterocyclic compounds. All right, so let's look at some examples here. Heterocyclic meaning that they don't just contain carbons and hydrogens, but there's some other non-metal in that ring as well. All right, so let's take a look at two examples. These 7-membered rings are a huge pain in the butt to draw. Good enough. All right, And so we're going to apply our rules for aromatic, anti-aromatic, non-aromatic, and classify these heterocyclic compounds as well. Okay? One of the keys here is going to be one thing that I'm missing in my structures here. We're going to be really good and make sure to put in our lone pairs. Nitrogen with its 3 bonds has 1 lone pair. Oxygen with its 2 bonds has 2 lone pairs. We're going to see these lone pairs are kind of the key to our classification here. Okay? So, rule 1 was which one? We have that fully conjugated ring. All right, so we need to go through and see if everything here is sp2 hybridized. And we can identify these 4 pretty easily right off the bat because they are a part of that carbon-carbon double bond. All right, so now our question is, what is the hybridization of that nitrogen? All right. And we're going to kind of boil this down to one simple rule here, which is lone pairs get to choose. All right. This lone pair of electrons right here on this nitrogen gets to decide whether or not it wants to live in an sp2 hybridized orbital or not. All right? And the way it's going to make that decision is based on whether or not that makes this molecule aromatic. Right? So this lone pair of electrons gets to choose. All right? It will be sp2 hybridized if that makes the compound aromatic, or that nitrogen is just going to stay sp3 hybridized if it would make that compound anti-aromatic. All right, so before we can really finish up our discussion of our hybridization here of each of these atoms, we then got to move on to rule 2 and see whether or not adding this pair of electrons would make this ring aromatic or anti-aromatic. All right, so we have 1, 2 pairs of delocalized electrons in those pi bonds. If we included that lone pair, that would make that 3 pairs of electrons. So is that going to make that compound aromatic or anti-aromatic? Aromatic, so great. Then this thing is going to go ahead. Nitrogen's like, I'll take that sp2 hybridization then, and I'll put that pair of electrons in a ring, or in a p orbital actually, so that it can delocalize about that ring. So in this case, what is its hybridization? It's going to decide to be sp2, because that would make that ring aromatic. All right. If we go on to our other example here, our oxygen. All right. Importantly, oxygen is going to have 2 lone pairs in its most stable state when its formal charge is 0. Importantly, only one can interact with the ring. Just because of the geometry of these hybridizations, you can never have 2 lone pairs that are sitting in the same p orbital, right? So one of these lone pairs here will always be localized, meaning it's just going to stay put on that oxygen atom. All right. So I'm going to go through and I'm going to ask myself, do I have a fully conjugated ring? So these ones are going to be sp2 hybridized, right? Everything about my double bond is easy to spy here, okay? When I get to my oxygen here, all right, again, it's got 2 lone pairs. I'm going to ignore one of them. One of them is always going to be localized. But if I look at the other one here, I want to ask myself, is that oxygen going to choose to be sp2 hybridized? All right, and again, we got to figure out whether or not that pair of electrons would make this ring aromatic or anti-aromatic. Okay, so we're going to start counting. 1, 2, 3 delocalized electron pairs. If we included the lone pair, that would be 4. So is the oxygen going to want to have that electron talk to the rest of them? No, it's going to keep it separate, right? It's just going to point that, it literally is going to point that pair of electrons away from the ring rather than adding it to that ring. So instead, that oxygen just simply won't be sp2 hybridized. It'll be sp3 hybridized. Okay, and let's just note, this is now sp3 hybridized. Because otherwise the ring would be anti-aromatic. But since it's sp3 hybridized, it's going to break that ring's conjugation. So is this going to be anti-aromatic? No, it's just going to be non-aromatic, right? So it's going to break the conjugation in the ring rather than making it less stable and anti-aromatic. So this one would be classified as non-aromatic. All right, your lone pairs get to choose whether or not to participate in the conjugation of the ring or not. They'll only do it if it makes that ring aromatic. If not, they're just going to sit out. They're not going to play the game at all. Okay, so let's see if we can't apply this now to another heterocyclic compound. All right, so in addition to calculating classifying as either aromatic or anti-aromatic, we can count how many delocalized, or I guess I could even ask you for localized right, so let's go through and count here. We need to see if we have a fully conjugated ring. So everybody about this 6-membered ring is sp2 hybridized. We also have these two over here about that carbon-carbon double bond, so those are sp2 hybridized. But now we get to our heteroatom, right? And before we can figure out whether or not this oxygen is sp2 hybridized, we got to figure out whether that pair of electrons wants to communicate with that ring or not. So we're going to count. 1, 2, 3, 4. All right? Is that pair of electrons going to want to talk to the rest of the ring here? Yes, because that'll make that into that, nope, can't count, into that odd number of electron pairs. I'll now have 5. So yes, that oxygen's going to go ahead and be sp2 hybridized, making that ring aromatic. All right, how many of those pi bonding electron pairs are delocalized? All of them, yep. What about my lone pairs? Just one, right? One of them on your oxygen can be delocalized. The other one always will remain localized. All right? In this case, I don't have any pi bonds that are not localized. Okay? And then lastly, our triangle with the nitrogen at top here. Is this one going to be aromatic, anti-aromatic, or non-aromatic? That nitrogen is not going to want to put that pair of electrons in the ring, so this one will be non-aromatic. All right, in this case, that pi bond is not conjugated with anything else, so they can't delocalize at all. I just have one pair of localized pi electrons and one pair of localized lone pair electrons, right? They're not talking to one another at all. Cool. All right, we will pick up, finish this off next class.